before we get into what we're going to talk about today, I want to go back, and I forgot to do something last lecture. Okay, and this is when we're talking about Monte Carlo simulation. And so we have a particle here, and it has a probability of jumping in one direction or the other. So P plus and P minus. Okay, and we motivated this from showing it's exactly equivalent to the Brownian dynamic simulations when we have constant jump. Okay, so I actually want to go through and show that this still gives you the proper diffusion result. Okay, and so this is an exercise we actually did in math. Is what to do. So let's start with all of our particles here. Okay, we're going to have a grid space like this on either side, and our grid spacing can be A. Okay, and then what we want to calculate is the mean x at each position, or at each time, sorry, and the mean x squared at each time. Okay, so if we put time here, this is t equals 0. So what's the mean x? T equals 0. Here. What's the mean x squared? 0. Okay. So now these particles are going to jump right or left. So how many of them are here? Half. Okay, so the probability of finding a particle here is going to be 1/2. And how many are going to be here? What's the probability of finding a particle there? 1/2. Okay. And all other sites, what's the probability of finding a particle? 0. So what is my mean x here?
It's still 0.
It's still 0.
That's
how about
nice.
my mean x squared?
1/2. So it's not 0.
So it's going to be 1/2 times a squared plus 1/2 times negative a, which equals a squared. Cool. So that's at t equals 1. How about at the next time step? How many particles are, let's start here. How many particles are here? Quarter. So probability of finding particle there is 1/4. How about here? 0. How about here? 1/2, right? Because we get a quarter from this side and a quarter from this side. And here? And here? Sorry, these look like ones. They're all just lattice. Okay, what is the mean square displacement here? 0. And how about, or sorry, the mean displacement is 0. The mean square displacement?
1/2 square plus quarter.
No, we've got to be careful. So the quarter, what's my a there? What's my distance?
2.
Yeah.
Well, negative.
Okay. And my 1/2, what's my distance there? 0. So it doesn't actually contribute. Right? Plus a quarter, and what's my distance here?
2a.
What does this equal?
Still 8 squared.
2a squared.
Oh,
Right?
yeah,
So we
yeah.
have 4 plus 4 is 8. 8 over 4 is 2. Okay, let's do one more. T equals 3. What do I get out here?
1/8.
8. What do I get here?
0.
What do I get here?
Hold on. 3.
8 plus quarter. Okay. 8 plus a quarter is
I got it.
3.
Oh no, I did get it. Yes.
How many here?
So happy with myself.
Here. Here. And 1/8. I just sound so bored. Okay, and how about our mean x? And how about here?
Still 0.
0. And here is going to be a big mess. So we're going to have 1/8, and we know we're going to have 2 of them. They're going to be equally spaced. Okay, so we're going to have 2 on 1/8 times
3a.
3a.
No,
3
sorry.
-3, -3x.
Well, we put the 2 there, right? So one of them's positive.
Okay.
Oh yeah, yeah, it doesn't matter.
It really doesn't even matter though. So.
Okay, my next term is the 3/8. I'm going to have 2 of those. And what is my distance there?
A.
A. Okay, what does this equal? Well, 2/8. So let's actually leave that as 2/8. I'm going to get a 9 here. I'm going to get, what, 18/8? Right? Plus, what do we have here? 6/8. And that's all a squared. And what does that equal? 3 squared. So are we seeing a pattern?
Let's do another one.
Delta x squared is equal to the mean of x squared minus the mean of x squared. Okay? It's equal to, this is always 0. And what we see here is that this is our time. Okay? It's just a squared times some times. Cool. So we know that this is equal to 2 dt. Right? So what is the diffusion coefficient?
A squared over 2.
And in general, that's if we have a time step of 1. Okay? So whatever we pick our time step to be, we can just multiply that down. Cool? Is this all right with everybody? Yeah? Okay. Let's think of another way to do this. So when we looked at the second order Landau equation, when we had inertia,
Tau's the time step? Well, like, wouldn't that cancel with the t?
Yeah, well, okay.
Because there's tau and there's t, but I'm asking you whether they cancel. I think so. That would in a discretize.
Yeah, it's discretized, right? Then we say we're defining tau to just be basically the integer that we're at, right? So it's equal to 1. Then we have an extra factor of 10, which is our constant. Right? But this works out. Okay? We'll come back to this. Okay. So what's another way of looking at this? Well, if we do long-term dynamics, we can't look at short times because we're actually holistic at short times, right? But if we do the first order equation, Brownian dynamics or Monte Carlo, then you got a weird grin on your face also.
All right, continue.
Right. Then we know that this is true for all times, right? We always have diffusive motion. Okay, so what does that mean? Well, it means that we could have predicted this result because let's just take a single time step, okay? In the single time step, our mean x is going to be equal to this. And if p plus equals p minus, this equals 0. And by the same token, what can I write here for the mean x squared? Not more. You just answered.
I'm writing down what we just did. has space. No, so how many times?
This is the mean x. Now I just want to look at the mean x squared, right? So all I'm going to do is I'm going to have the same adding up the probabilities, but is it going to be multiplied by a?
Just do our jump space squared or
Just
a squared.
Exactly what.
Okay.
Okay, does that make sense to people? Yeah. Notice it's not the same thing as this square, right? Because then we would have a square over this whole thing. We'd have cross term the probability square. Okay. No, it's the square, the x squared value that we're averaging.
So we also just showed that our x squared depends on our time. So shouldn't we have to include something?
This is for a time step of 1.
Oh, just for
Yeah,
one?
yeah, yeah. Okay, so this is all for one time step.
Okay. I'm okay. I'm happy.
Cool. Okay, well, what is this equal to? P plus equals P minus equals 1/2. This is it's just a squared. And then we know G is going to be equal to our delta x squared over 2 our time. But our time here is just going to be 1 time step. Okay? And so what is our D equal to a squared over 2? Okay? So we can get this directly from the probabilities. We don't actually have to do this chart. Okay? Cool. But here's where our time comes into it. Because if it's one time step, it could have some different unit. Okay? This can have a different unit in there. Tap. Same here. So it's one time step, but that time step can have some units, right? It can be a metric step. Cool? All right, so we should have done this last class when we were talking about Monte Carlo. I want to do it because we're going to need it at the end of this class today. Okay, because we're going to come back to these kinds of arguments. All right, and this is a simple case. So are these two things cool with people, what we're doing? Yeah? Okay, great. Okay, so let's go back to what we were talking about. And what were we talking about? We were talking about adding a drift to our simulations, okay? So we had non-equilibrium simulations now. Everything we've done up to this point was for zero external field, and now we're bringing in an external field. What have we seen? Well, we've seen that it's really easy to add a force to our longitudinal dynamics or Brownian dynamics simulations because these are based on an equation of motion. The equation of motion is ma equals the sum of the forces. So we can just add the force. And we can have whatever crazy dependency we want. It can depend on position and velocities and time, anything you want. As long as you can calculate it, you can numerically integrate it. That's the point. Okay? We saw for an easy case where the force was constant that we had really just a Fokker-Planck with drift with the Gaussian that both spread and move. Okay? And that's it. So we talked about calculating diffusion and drift. And so I want to use these ideas now, and I want to talk about, this is a good place to talk about boundary conditions. Okay? And so boundary conditions, and the first one I want to talk about are reflecting boundaries. Okay, so RBC. reflecting boundary conditions. What do I mean by reflecting boundary conditions? Let's consider a system, as we have been, where we start a whole bunch of particles at the center. Okay? And up until now, we've been really simulating on an infinite domain. Okay? We haven't added any boundaries at all. We just make sure the simulation, it doesn't go long enough that we run out of space in our allocated array. Right? We have an arbitrary shift of 500, as long as we don't go over that. Let's actually put in some boundaries now, so that we have a point. Okay. So I'm going to put a boundary here. Here. We can call this, let's say, L, and so this will be L over 2, and this will be negative L. And I want these to be reflecting boundary conditions. Okay. What do I mean by that? Basically, these are infinitely high walls, you can think about. Okay. The balls cannot jump and get out over these walls. So what happens is when a particle hits here, it's reflected on. Okay? And we've talked about coding this before. What you do is if a particle jumps over the wall, okay, first thing you do is you reverse its velocity. That's a reflection. And to take care of this, you can calculate this shift here and move the particle the same on this side. And then it's just like at a perfectly elastic collision. Cool? Super easy. Yeah? So what's going to happen? This distribution over time.
So at first, when it's not touching the wall, it'll appear like a regular density that can spread out and do everything you don't expect it to do.
Yeah.
But it hits the wall, it starts acting as a whole, and then it becomes a uniform distribution.
Right. Okay. So what do we expect the long-time solution of this to be? Just a flat distribution. Okay. And so here's one of the handy uses of reflecting boundary conditions. Allows us to calculate the steady state configuration of the system. Okay, because given enough time, the system must approach this. Now note, this does not mean that we give it enough time and every particle is like, okay, you're here, okay, I'll go here, you're here, like birds on a wire, and then they just sit there. Okay? This is dynamic equilibrium. Particles are constantly moving back and forth. Okay? But at any one time, on average, there's as many going in one direction as the other. Okay? And so, of course, depending on the number of particles, you can see ripples on the surface. Little fluctuation. Okay? But no, not rogue waves. Okay? We need something different for rogue waves. Cool? Okay, the more particles, smaller particles. Okay? Yeah? Okay. So let's just quickly look at some code to do this. So I'm going to do longevity dynamics for this part. And the other thing that's interesting, okay, which is actually what this chapter is about, this is true in the zero force case, right? But we can easily do the simulation where we actually have a force biasing this in one direction. Cool. And so let's say I do a simulation. Where again, I'm going to start with all the particles here. Yeah. Terrible. Okay. But I'm going to have a force in this direction. Now, what do you expect it to look like? Constant force. Okay. F of x equals F naught.
Wouldn't you expect to move right and get wider distribution at longer times, and then you see them all against the wall? You'll see something like that on the very right side of the wall.
Okay, so first of all, let's talk about short time. What should this look like at short time?
Shift right.
It's exactly what we talked about last lecture, right? If both the mean goes to the right with the direct velocity, and the distribution itself spreads into time. Okay, so both the mean and the variance of the distribution are time. Cool. What happens when it starts to hit the wall? Okay, so at a later time, we expect it to have spread. Okay, and also the mean shift right, so looks like this. Now it starts to happen.
Couples back on itself. So
Yeah, what does that mean?
the edge close to the wall is going to start rising up, and the other edge is going to look still pretty normal.
Yeah. And how about this? I mean, because we have this force, do we not get a steady state solution anymore? Or does this still approach
No,
some kind of steady state?
We still get a steady state, but it's
What does a
not.
steady state look like?
It's not a uniform horizontal line. It's just going to be. It's going to have some thicker slopes. So maybe like some line angle.
Okay, so
I don't think it'll be linear. I think it'll be Boltzmann.
Martin.
Still have to have the, we still have the thermal.
How's it gonna look like that?
Maybe not perfectly to zero on the far side, but more like that-ish.
Okay, so
Like I
both
think-
or linear. Any other guesses? You shouldn't have to guess. Statistical physics, but it's statistical. If you have an energy landscape, which in this case, it's like that. What do you expect? Distribution, particles is a function of x. Pardon me?
Even minus.
Yeah, so it's a negative ux over kt, right? Yeah. So that means it's e to the epsilon x. Cool. So is it a straight line? Okay. The next one. Expect it to look something like. Cool. Is that okay with people? All right. Again, Boltzmann, super important. Okay. Boltzmann factor, super important. Okay. Why does it look like this? Like, what the hell am I talking about? What if I take a bunch of tennis balls and I just drop them? Right? Is that not this scenario? I don't get a distribution of tennis balls. Right? They all just. What's the difference between that and that?
They're still like BFFing.
Exactly. Okay, that's true when diffusion is essentially zero. Okay, when diffusion isn't zero, when diffusion is non-negligible, then not everything ends up on the ground. Okay, because if there's thermal kicks, then we know that we have an effective force, right, that wants to go from high distribution regions to low distribution. Okay, and that's how, the force wants to push them here. All right, but basically an entropic force that says, no, I got some thermal energy here. I'm not going to hang out here. Everybody's here. Really anthropomorphic.
Good.
Cool. And this is the kind of balance we end up with. All right.
So that's the long-term uncertainty because of the reflective.
That's a steady state
yeah.
solution. Cool. Okay, so in order to do simulations of this, we can do our usual non-German dynamic simulations, which is what all of this stuff is. Two things. I have this force in here that I just include as a term in the acceleration. Okay, very complicated. And then I have my reflecting wall conditions here, right, where I'm just, in both cases, I'm flipping the velocity, and I'm also just taking how much has gone by the wall and putting it that much on the other side.
Okay.
Cool. And that's it. Is this okay with people? So now, since I have a finite domain, I don't have to do crazy things like shifting things by 500 and making sure my simulations don't run so that things go beyond 500. Okay. I have a nice finite domain. I can just make an array row, which for some reason is still gigantic, but I'm going to set my L equals to 20, so that basically my simulation go from -10 to 10. Cool. And what do they look like? So let's see. How do I do this? Okay, so this is just a data file produced from the last program. Okay, and here's what it looks like as a function of time. This is for the F0 case. Okay, so this is the first one we drew up on the board. And as we saw, initially we just have a Gaussian that's spreading, staying in place because we have no external field. But now it's starting to hit the wall, and so we see the edges rising. And if we wait long enough, it'll be a flat line. So test our patience. For you. That's
Yeah, it's flattish.
flattish, eh? Cool. Now let's do the same thing, but
Just a question for that one. Is it because of your conditions that on the left hand or the right hand side are different down to 0?
it's a binning issue.
Yeah, okay.
Yeah.
Or no.
Now let's so this is force 0. Through all my errors. Let's stop the program. Let's do it with the force of 1. Oh, I really should have skipped that. Oh, no, I don't want to. Okay, so here we see it's hitting a wall, and now it's really spreading up on the wall. So you can actually get some really interesting intermediate, some transient distributions. Okay, but now we're going to approach an exponential. It's not going to grow forever. It's actually going to slash. Cool.
So what does it look like if you bring the wall in way higher? Like here, the exponential is basically 0 when it reaches the other wall. Does it look like it's not 0 when it reaches the other?
No. Give you some code. Write some code. Okay.
If you drop the force right away after that, would it just go back the other way or?
Yes. Yeah.
Or
If
there's
you
still,
drop
like-
the force,
Yeah, right away.
then there would be no flux of particles due to
Yeah.
the force this way. So the flux of particles due to Fick's law this way.
Yeah,
And the only flux, and we've been back with the flat distribution.
would there still be like a shape, like, depending on how small the distance of length to the wall, where would it go up the other side of the wall? Because there's more going back this way?
Yeah.
Or do they not inject it all?
It's unlikely that that would last that long.
Yeah.
I think you just see that thing go down. You might get some interesting, but I don't think it would be so dramatic as a sloshing over.
Yeah,
and coming
depending on
back.
how small it is.
Because inertia is not that
Yeah.
big on that scale. So, just to convince you this really works, here is a plot showing different times. So this is at very short time distribution, still short time, more intermediate time. It hits the wall and starts building up. And the solid black line is just the exponential that we would expect from Boltzmann distribution. Okay? It's just e to the x squared, and then shifted by 10. Cool? Okay. So those are reflecting boundary conditions. And it's cool because they can tell us stuff about statics. Okay? What's the long time solution? But they aren't the only boundary condition we have. So if it's not reflecting, what might it be? The other extreme?
Periodic?
Oh yeah, there's periodic.
Yeah.
But we're not even going to talk about that today.
Just a static boundary condition.
Periodic boundary conditions are just a coding cheat. What's another physical example?
Just like a static boundary condition, like if you're at like L over 2, it has to be a certain number.
Yeah, okay, so that's more complicated.
Oh, like
Okay, so that's like
fixed.
if you were like to allow a certain flux of particles to or something.
Okay.
Yeah. But what's the other extreme from reflecting?
absorption.
Yeah, absorbing. Okay? So what if instead of you hit a solid wall and you bounce off, what if it's like an electron hitting a metal plate or something? It's absorbed. Cool. All right.
And we're just doing reflection, like straight back and forth.
This is all one dimension.
Yeah, there's.
So now, if I start with a distribution in the middle for absorbing boundary conditions, okay, again at L over 2, negative L over 2 to L over 2. What's my steady state condition? Yeah, but we have a flat line.
No, I meant like at nothing. Like,
Yeah, you're zero.
Yeah, because
But in
I'm
steady state condition is there's no particle. Okay, eventually everybody gets absorbed by the wall. Cool. So this actually introduces a whole different class of problems. Okay, seems like a trivial change, but what we're not interested in is the distribution and the steady state distribution and things like that. But now what we're interested in is how long do these particles survive in here? What's the survival probability? Or how long does it take on average for a particle to hit this wall? For a particle to hit this wall? So we're not talking about statics anymore, we're talking about dynamics. Cool. In fact, this is a very universal class of problems. And you can really look at it, if I start a particle at some location here, how long is it going to take to hit this wall? How long is it going to take to hit this wall? Okay, and this is known as the mean first passage time. And that would be okay, so we've talked about our ion. Can you think of any other examples where mean first passage time is the rise?
like in your body.
Whatever you want.
Like drug absorption.
Sure.
Mixing things together. Salt
Sure.
and sugar, dissolving it into water.
Right. We can even think of our drunk walking home after the bar doing the random walk. It's really mean first passage time. How long does it take him to get home?
Or to the next bar.
Right? Or to the next bar. Okay, but there's a terminal event. Once he's there, he stops. Okay? A lot of problems, I'm not going to say most, but a lot of problems have a terminal event associated with it. Okay? And so a lot of things can be recast in terms of mean first passage. Okay? And we talked even some more extreme examples, like how do you make a decision? How is an opinion formed? Okay? You can have fluctuations, but eventually you make a decision. Okay? There's a terminal event. Okay? So we can ask, well, how long does it take you to make that decision? Okay? Well, it depends on all the uncertainties. If you're weighing lots of pros and cons, there's lots of variability, it might take a while. Yeah? Cool. Okay. So what does this code look like? The program is really similar. The analysis is a little bit different. So our program can look the same. Okay, all I'm doing is adding this force to the acceleration. Oops, this is the wrong code.
The folder's getting really big.
Yeah, no, it's a crazy one. Okay. So again, I'm just adding this force to acceleration. And now again, I'm checking for my boundary conditions. But now when the boundary conditions are reached, we need to do two things, okay? I'm going to count the number of particles that have reached the boundary. So I'm going to keep track of that as a function of time. And I'm going to do that for both the right and the left. And I'm also going to keep track of how long it's taken for the particles to hit the boundary. Cool. I'm just keeping two running sums. The number hit right, number hit left. And I'm just going to keep adding up the time so that at the end I can divide them by the number that hit right and the number that hit left. And when I do that, I will get the average. Okay? So I can keep track of the probability of hitting each wall. And I can also keep track of the mean first passage to each wall. Cool? All right. So let's see what this looks like.
So you're not necessarily finding out, like, you're not necessarily removing them from the simulation, but you are just saying, like, when they pass this point, I'm just going to count.
Yeah, no, but I am removing them from the simulation too.
Are
So
you-
I stop integrating over them when they've hit either of the walls.
Okay.
Okay. So we can see that what the distribution looks like here. When it hits the walls, you know, there's a binning problem here. I should shift this by half, but both of them must go to 0 at the wall. The boundary condition now at the walls is that there's 0 particles at the wall, because any particle at the wall is okay. It looks like a Gaussian spreading. Then when it hits the walls, it goes to 0. Cool? And so as time goes on, this distribution is just getting lower and lower. Okay? And to answer your question, Austin, so there's another if statement here. I just keep track of which particles have exited the system. And then when that is equal to 0, then I integrate over them. When they leave, I set it equal to 1, and then I don't look at them anymore. Okay? Okay. Let's do the same thing, but with a force of 0.5. See what happens. And so again, in the beginning, before it hits the wall, we just have our traveling Gaussian. Now it's going to hit the wall. We'll actually get quite a buildup of the wall. The stillness goes exactly to 0 there. This is kind of what it's cool. Okay. So the distributions are not actually what we're really interested in. What we want to know is about these mean first passage times. Okay, so here's what the distributions look like. But here, I'm going to plot the number that goes to the right-hand wall as a function of the external force, okay, in red. So when the force is 0, and this is a number that goes to the left-hand wall, when the force is 0, we get an equal number going in either direction. Cool? As I increase the force, the amount going to the right-hand wall increases, because I'm driving them in that direction, and the amount going to the left-hand wall increases. Cool? Fair enough. You can derive what these dependencies are. And it's pretty neat math, survival probabilities and stuff like that. It's a very excellent. Okay? Mean first passage time problems. You can also derive where you start in the domain. Okay, if you start really close to one wall, how much more likely are you to hit that wall than to hit it? It actually just turns out to be linear at the distance. Okay?
Is that the time start? Or is that how much
Force.
Okay, yeah.
Okay. But now I have a question for you guys. Okay? This is the force. So this is the probability of hitting either wall. Okay? Now, how about time it takes to hit either? What do you think that should look like? So the mean first passage time to the right-hand wall and the left-hand wall. Remember, our force is driving particles towards the right.
Yeah, the force increases by time.
Pardon me?
It's such a huge force, it's going to be so long to.
Okay, so first of all, let's talk about the time, the mean first passage time to the right hand. How do you expect that to be a function of force? Not a good question.
Force increases, right? It's gonna go down to 0. Or,
It's going to decrease.
Yeah.
Right. Let's not worry about the exact form right now, right? But if I start on my particles in the middle, and I have force in this direction. As I add stronger force, they're going to get driven harder to that wall. The time's going to go down. Right? Cool. We're all okay with that. That's how about the time to the left hand? Driving it in this direction. Sarah's answer. What's your answer?
So do longer, but
Any dissenting opinion?
time, depending where you're starting from.
Everyone
Well,
starts
it's
from the middle.
Yeah, so that's like different time.
Okay, so your answer was takes no, we're looking at the mean first passage time. The average time it takes to get to the
Is there distance there?
Yeah,
So our job, are we, it's long, I guess, like.
It's a Longevin, yeah.
Average over the particles that actually make it.
Well, it looks like it's going to get 0 here, okay, but we still have some that are making it.
So we're taking the average time it takes those particles did make it.
Yes.
yeah, there's a positive.
Yes.
So should we?
No, because in time, so basically you could make the argument that if they don't start going there right away, then the longer the simulation goes on, the less likely they are to ever make it.
Yeah.
So you're averaging over a biased sample that had to have reached that wall first. So it's possible that it would go down or that it would stay constant.
No force 3 equal.
It's a very good physical argument. I think you're absolutely right. Okay. So we can talk about the conditional and unconditional times. Okay. Now the conditional times, these are the ones that make it. And if you plot the mean first passage time to either wall, times are about the same. Okay. We obviously have some error here because a very small number of particles that make it. Okay. But the time is actually, it goes down with force. The time to either wall is the same. This is exactly what Martin said. Okay, if you have a strong force driving you in this direction, unless you boogie this way right away, the longer you hang around, the more you're going to be stuck to that wall. So the only particles that make it to the wall are those at the stochastic path that there's a heavy bias to that wall in the stochastic path. In other words, it gets a lot of kicks in that direction. Cool. If you get a lot of kicks in that direction, you're actually going to go that wall.
Faster, yeah.
Cool. Times turn out to be this.
Yeah. Is there any kind of representation towards that cake where you go from the one slope to the next?
Although I only have 3 data points here.
Oh, sorry.
You could plot this out and it would be smooth, right?
Okay, never mind. Sorry about that. I just thought I was like, wow, this is a really kind of crazy cake.
No, no, no. So again, I don't want to do too much based on the process of the project. Okay, and you can actually work out the functional form for these different.
Alright.
Cool. Yeah. All right, and this is also important stuff if a person decides to do fusion in one dimension where we have different viscosities. Okay? Because this is a way you can put finite system and you can put reflecting boundary conditions there, and you can look at the long time equilibrium distributions that you get. You can put absorbing boundary conditions there, and you can start calculating the probability of going to either wall and the time it takes you to get there when the viscosity is different on either side. Cool. And in general, mean first passage times, now that you know the word, you'll start to see it all. Okay? It really is a way to model so many systems. It's quite hot these days. Cool? Good with this? Okay.
Yeah, wait, should we do more data points? They wouldn't appear linear like they do there. They have to come up more like.
I think that one might be linear, but I'll let someone else answer that question.
I was just curious how I was writing my set.
That's the number of particles, not the time. So I want to talk about something else. And to do this, when we're talking about all these simulations, right, we start with a zero force, and then we apply a stronger and stronger force, and we see that behavior changes significantly depending on the force. Okay? In fact, we have two physical mechanisms here. We have diffusion and we have drift. And we can get very different dynamics if we go from a diffusion-dominated regime to a drift-dominated regime. Right? When in a diffusion regime, your mean square displacement goes as t. If you're in a drift regime, the mean square displacement goes t squared. Okay? All the things we talked about. If we're in a diffusion regime, equal number of particles will hit either wall. If we're in a drift regime, all the particles will hit. Cool? So it's important to know in many physical systems what the balance between diffusion and drift is. Okay? Even if we're not talking about particles. Even if we're talking about stock prices. Okay? We want to know what the balance is between the interest rate and the volatility. Okay? How much are things fluctuating to how much things are going in a steady way. Cool? Okay, so the way of characterizing this is the Peclet number. Okay? Peclet number is a dimensionless number, and it's the velocity times L over the diffusion coefficient, where the velocity is a measure of the driven aspects of our system, right? Because this is the drift velocity. And D is a measure of the diffusive aspects of our system. The bigger the D, the more fluctuations. Cool. And what are the dimensions of velocity? Sure, SI units, meters per second. What are the dimensions of this guy? Remember? D?
Of D?
Yeah.
Meters squared.
Meters squared per second. Right? How do we know that? Because delta x squared equals 2 little d, big D. Right? The units of D are meter squared.
Length is a meter. Got that?
Yeah, very good, Austin. So for this to be dimensionless, we need a characteristic length in there. Okay? And then we can get a dimensionless number. All right, and we'll talk about why that characteristic length is important in a minute. Okay, but it's a dimensionless number. So basically, if your Peclet number is very big, what you expect the dynamics in your system? Drift, right? So you'd expect mean square displacement to go to t squared. You'd expect to have a really noticeable change in the mean position. Okay. If you're looking at absorbing walls, you really expect particles to go in one direction. Okay? If your Peclet number is much smaller than 1, diffusion. Okay? And so you wouldn't expect the mean square displacement goes as t. Cool. And likewise, we wouldn't expect a strong preferential direction in absorbing walls. Okay? So got a program here. I think I do. Okay. So this is just a longevity dynamic simulation for a single particle. Okay. And what I'm going to do, we're going to have our standard values here of KT1, friction coefficient of 1. And so remember, D is equal to KT over zeta, right? So this means our diffusion coefficient is 1. And we're going to have a force of 0.1. All right, and so we're defining characteristic system size to be L to be 20. Okay? And so if we run this simulation, let's see what a little bouncing ball looks like. Oh, okay.
there.
So it actually looks pretty drifty.
Yeah.
Okay. And so if we calculate our Peckley number, okay, T is equal to KT over zeta, right? And the drift velocity is equal to the force over zeta. So D is 1, and the drift velocity, if this is 0.1, this is 0.1. So Peckley number is 0.1 multiplied by 20 over 1. Okay, so it's 2. The drift is slightly dominant. We can see this thing bounce back and forth, okay, but we saw that drift determined what direction it went. Cool.
Where do we draw the line with the Peckley number?
It's around 1. It's dimensionless, so it really is around 1.
Well, like the Reynolds number is like at 10,000. Like that's the threshold.
Reynolds number is more complicated because there's prefactors in there, right? Objects that depend on the nature of the object and stuff like that, right? Like if you actually do the calculation, it's in Young book, right? That the mechanics book.
Oh, okay.
Is it Young? Taylor.
Yeah.
Yeah. Because if you actually do, Reynolds number is basically related to if you do the quadratic drag over the linear drag term.
Yeah.
Right? And so that actually depends on the nature of the object. So the Reynolds number is close to that, but Reynolds number doesn't have those prefactors in it. Right? So depending on the object, how close the Reynolds number is to that actual ratio can change. Yeah. Okay. So let's do some stuff. So let's change our force to be 0. What do you expect to happen? It's going to be just diffusion, right? Let's not even bother. So actually, let's keep the force at 0.1, but let's change KT. Question: the simulation looks to be stable. I think I may have shown the wrong movie a minute.
Yeah, no, wasn't definitely.
Okay, so now drift is not nearly as dominant. Okay, the fluctuations are gigantic. Okay, and so if we want to ask the question, which wall does it hit? Well, we're at a low Peckley number where diffusion is going to kind of shrug. If we're at a high Peckley number where it's driven, then we can say correction. Cool. And in terms of the time, if it's driven, it's going to be a shorter time than diffusion, right? It takes a while to find things like that. Cool. Okay. Let's bring KT back down to 1, and let's keep our force at 1. Let me redo the simulation. I'm not sure it was right. So that's one where diffusion was definitely dominant. Okay, yeah, so this is more what it looks like. So this is our case where we have a Peckley number of 2. And here, they're about equal, the contributions from drift and diffusion, okay? Because there's still quite a bit of variability in this position. Cool. But now let's turn down KT even more.
I think I'm oh, KT 200. Pretty sure it's just make it a face. Yeah. It's pretty much going to go straight.
There's still some case, okay? But drift is definitely determining where this is. Cool. right? So that's cool. We've motivated this nicely, but how about L? Why is L on there? Because what L says is, if I go from having like these other balls 20 apart to only having them 2 apart, the Peckley numbers all come down. Does that make sense?
Except for the diffusion always wins on short time scales.
Yeah, that's exactly the reason. Okay, diffusion wins on short scales. Okay, because you have these thermal jumps that are of a certain size. So even on very short time scales, you're going to be jumping around. Even though on those short time scales, the force is barely moving. Okay,
You can get a strong force.
well, that's just the point of the crossover. Okay, but there's always a crossover from diffusion to drift up. Okay, and so L is basically accounting for that. Cool? Yeah? Is this all right with everybody? Okay, Peckley number, really useful. Okay, so we've taken our simulations, we've added a force now. Let's add a non-constant force and see what happens. Okay? So, let's say we have a force that depends on our position, which is not a crazy proposal. Very hard to get constant forces in nature. Kyle something. Okay, and so this is what we would get. How much harder does this make our life?
So that doesn't change in time.
Not right now. Not right now. We throw up our hands. It's Thanksgiving weekend. Let's all just go home. This is too hard.
Well, numerically, it doesn't change a lot.
No, numerically, it doesn't change at all. Okay, we know our position. That's what we're trying to solve numerically. So we can totally calculate our f at any x, right? As long as we can do that, instead of just adding a constant number here, we add a number that depends on our x position. Who cares? I can do the same thing. I calculate a, b, x. Cool. This is why simulations, especially longitude dynamics and Brownian, are so powerful and universal and robust, and molecular dynamics as well. So you can add, as long as you can describe it as a force, you can add anything to the system and let it go. So let's do a case. All right, so let's do a potential landscape. Okay, and I want potential landscape. Yeah, I want it to look like this. Okay, so my u of x, you can see it there, is going to be equal to some coefficient times x times cos 2 pi omega x. Okay, and that is what this red curve is. Cool. So my energy, when I'm here, I'm going to have reflecting boundary conditions, so it's in a little bit of a well. It's at an unstable maximum here, minimum here, maximum, and this is a global minimum, and global maximum. Cool. Okay. Well, how do I bring this into my simulations?
Is the derivative of potential of
Yeah. F of x is just negative d dx u of x. Okay? And And that's what's shown in blue here. Cool. Okay, and so that's what I need to bring into my simulations. And so that's this thing here. Details of it don't really matter. It's got an a times our cosine term because the x just goes away. And when we take the derivative of the other term, we have our ax out front still, but we pick up a 2 pi omega. Cool? And of course, the cos becomes the sine. So in my program now, previously, I was able to just add in an f over g term, where f was a constant value I assigned at the top, right? Now my f is dependent on my x position. So for whatever particle I'm looking at, I can just analyze what that f is equal to. Cool? And then just bring it into the simulation like that.
What are the boundary conditions?
Reflecting. Because I'm going to use reflecting boundary conditions because I want to look at the steady state solution. Cool. And there actually should also be an m in here, shouldn't there? But I'm setting m equals to 1, so I can change it. It is just f over m.
So we can just throw like any crazy landscape of like views in there and just take the derivative and go. That's pretty cool.
Yeah.
If things get really messy, then you might run into particles.
That's the fun part.
Okay, so
And if you really need to tell me
so pop quiz. This is my potential landscape, right? Can you? What did you just say?
Nothing.
Pardon?
Nothing. I'm anticipating your question, but you can't tell me not to answer because you haven't answered.
Pardon, no pre-answer. No, what is my distribution going to look like?
I said nothing.
Anybody?
So, from my lessons learned, it's not going to be linear.
Can we predict this?
We can with a little bit of effort.
So how many particles are we going to have at this position? Remember, potential landscapes are sweet because you can literally consider it to be a ball on a hill. All right, the balls on that hill are going to want to stay there if there's some wind bouncing them back and forth.
We should very
How about here?
Once again, very few.
Yes. Yeah, but we're going to have like a lot here, right? Cool. And so we can actually quantify this. It is the Amber, someone help me out. The probability of finding a particle at any position x, where we have a potential that also depends on x, is Kyle.
What we already did. Oh,
Yeah. Okay. E. Wait, why do we want to say it?
I said it.
Well, he already told it to us.
No, I know.
So that's why I didn't want to say it. Yeah.
It's always both the same.
It is always both. It's the same answer every time.
Yeah, and I'm going to keep asking a question until the whole class can say it. Okay? Boltzmann is okay. Okay. So I'm not going to bother with the simulations. Let me just show you what it looks like. So if this is true, then what I get out of the simulations, so the red is taking my u of x that I defined up there, okay, and plotting the u of x. Oh, I don't need this. Oh,
E to the negative vector thing.
yeah. Okay, and then all I'm doing is I'm just normalizing it. Okay, the second factor is just normalizing it so the area underneath the curves is the same, so that they sit on top of each other. Cool. So I'm just taking the integral from 0 to 50 of that curve. Cool. And the blue is what I get out of my simulations. And again, I'm normal, but it's total number.
That's really good.
That's pretty good. Okay.
That ultimate guy knew what he was talking about.
Hmm. Cool. This all right with people? Yeah.
I didn't even think you'd use a Boltzmann distribution for stuff like this. That's awesome.
Everywhere.
Yeah, it really is all over the place. Cool. All right. Let's do one other thing in the same type of idea. And Martin, no talking at all. So, what'd you say?
Good thing I brought the
That's all.
model.
Yeah, that's perfect. Okay, so
He's wearing blue too.
So what we're doing is there's the, I didn't mean to. That's
Well, from out of the blue days, but I was saying it's a conservative.
Oh,
Puzzling and
He's going there already.
oh yeah. Friday? Yeah. Okay, so this is, we use the reflecting boundary conditions here. I might have, let me check. Oh no. Yeah, so when I do that simulation, I start with my particles evenly distributed between 0 and 50, okay? So my x position here is 50 times a random number between 0 and 1, okay? And so it's interesting to watch over time what happens. So they all start evenly distributed. So what's going on in the class? Everyone's like laughing. Are you guys like texting under the table or something?
No,
I think we're just like tired.
I'll smoke a weed.
No.
Almost Thanksgiving weekend. So it starts flat, but you can actually see it approach the Boltzmann distribution here over time. Okay? So this actually leads into the next thing. This allows us to look at the static distribution of particles. Okay? But how long it takes to reach the equilibrium distribution is also an interesting question. Okay? But let's make the question even more simple. If I have particles that start here, okay, and I want to know how long it takes to get over here, okay, and I know this energy height, and I know this energy height, and I know this energy height, okay, and we will want to take a guess at how long the scaling of that time tau of some of these energies. Let's call this A, E at position B, E at right, scale to go from there to times so to get from here. Times so we get from here over this to here.
The time step?
So this is like activation process. Right?
EV minus PA, or maybe no low depth.
Yeah. Okay, it's going to go as
And let's get KT might be well done huge, that it takes a long time, to make KT massive, that takes a very short time.
exactly. Okay. So no, because basically it goes as E to the barrier height. Okay, the bigger the barrier, the longer it takes. Okay. If you look at the frequency of hopping, that would have the negative. It's okay.
Does that come from something?
Arrhenius.
Yeah, Arrhenius.
That was in our class last week.
Cool. It's all right with people. Yeah. So let's try and do this guy.
R tedious.
So the barrier I'm going to pick, make our life easy, is just going to be a single peak, the first peak of a sine function. Okay? And I'm just scaling it so that it goes from 0 to 1. Okay? So this means our u of x is equal to a sine pi x over 50. Okay, and that's going to be from 0 with reflecting boundary conditions. No, actually, I don't even need reflecting boundary conditions. Okay, because I'm looking at the dynamics. Cool. All right. So again, I can bring this into my simulations. I just calculate the derivative of this, gives me the force, and bring that into the simulation. Okay. And when I do that, this is why I have so many programs.
So, so we want the potential landscape to be a hill, not a well.
Yeah, the hill. Yeah, because we want to look at basically the escape time. How long does it take to go from here?
So we're starting from on one side of the hill.
Yes.
The escape of a barrier or escape of a barrier side?
Escape over barrier sign, obviously. So
Come on.
here's my force in here. It's just cosine. Okay. I'm starting all of my particles up here at 0. Okay. And I'm going to keep track of how long it takes for them to reach 49. Okay. So obviously well on the other side of the hill. Cool. And I'm going to keep track of the escape time and also the number that have escaped as a function of time. Cool. And so if I do that, then this is the number that escaped as a function of time, and here is the average escape time. Okay, it's obviously plateauing up here. Cool. Now I can do this for different values of A. They just will scale the peak height, right? So if A is 2, then my barrier height is 2. And then I can plot what the distributions of time look like here for different A's, and I can also plot what the escape time looks like as a function of the barrier height. Okay? This is essentially just my coefficient A. And then this is the average time it takes for particles to reach, to go from 0 to 1. Cool? Does this make sense? Yeah, but I thought we said it was going to be an exponential. If I do it on a log-log plot, this isn't an exponential. This is the semi-log plot. Okay, so I'm taking log of them, and that's plotted linear in x, so it should be a straight line. Okay, so this is what we predict. So it looks like it's approaching that at large barrier heights, but there's a big deviation at small barrier heights as well.
For like small wells, you need diffusion, and larger wells, and it's like
Very good. Okay, this assumes it's totally not drift, but escape barrier dominated. That the dynamics are barrier dominated. Right? As the barrier height goes to 0, this says, oh, it doesn't take you any time to go from 0 to 40%. That's of course not true. You have to diffuse that. Okay, that is not in there. If you add that term to your Arrhenius thing, then you can get something on more. Okay.
so the barrier is too small in case you're giving it, but it's right open.
Well, if there's no barrier, right, it can just diffuse there, but that doesn't mean it takes 0 time. It still takes a finite amount of time to diffuse. So you basically have to add like a constant. An easy way to approximate it is to add a constant here. The time will take this one here. And then you get something that's close. Cool. This is also another good project. Right? Escape times, Kramer escape problems. And there's coefficients here that depend on like thermal energy, like an attempt frequency, right? And then you can simulate that and try and model it. Interesting stuff. And one of the interesting things you can do, I want to show this to you guys quickly, because it's super cool. If you have a potential, okay, so you have potential over a whole domain, and you want to figure out how long it takes you to go from point A to point B, okay, where this guy is u of x, okay, you can actually solve for that time exactly. The double integral, the first one runs from 0 to b. The inner one runs from negative infinity, and the upper bound is actually the argument of this integral here. Okay, and the sign split between the inner and outer argument. So it's negative the potential inside, outside, and it's just potential. Cool.
You use one.
Pardon me?
Oh, you do the inverse of the function, and then so the inverse of u in there.
No, it's not the inverse. It's just
You have u of y.
yeah. So this is integrated over a y, right? So
Yeah,
for
so-
each y value here, right?
Oh,
You first have to do this up
Right.
to y,
Right.
and then that you integrate over. Cool. Yeah.
Sorry, I thought you had to do like swap x and y. Never mind.
School of people.
Yeah.
So let's do the simple case of zero potential. We get
Then we just get like a minus b. B minus, sorry, b minus a. Okay.
squared, right?
Yeah.
Right? We get 1/2 b minus a squared. Does that look familiar at all?
I feel like it should.
That's just straight up diffusion, right?
There's two.
Cool. Yeah. All right. So this can capture the diffusive limit when the potential is 0. Okay. Yeah. Okay. Now this has a negative infinity in here, which can obviously be tricky to do analytically. Okay. But what we can do is we can change this limit to be 0. And if you look at the form, what that does is it says anything from negative infinity to 0 doesn't contribute. Right? In other words, u of x over that domain cool, such that e to the negative infinity is cool. If u of x over that to the left of 0 is infinite, what boundary conditions? Reflecting. This is an infinite potential, you can't get it. Cool.
Is one term supposed to be negative while the other term is supposed to be positive?
Yes. So here is what we get. So here's that integral in math. This is why I like math, because I can just do this in the middle. Okay. Here's that integral, and I'm doing it for different values of a here. Okay. And so the red is what I get from simulations, and the blue is what I get from that integral. Cool. In fact, there's a small deviation. I Is there a small deviation? Yeah, at the 0 time here. So it's slightly off in the 0th limit. To be correct for that, things even get slightly better, but it doesn't really matter. Okay, so this is really cool because it says you can actually calculate the mean first passage time exactly to get potential. Okay, and this was used in the first analytic studies predicting the scaling of the translocation time of polymer through a nanopore with the nanopore with the polymer. Okay, they constructed what the entropic barrier looked like, and then calculated the mean first passage time as a function of the polymer.
So they used free energy instead of energy?
Yeah, they use free energy. And they got the wrong answer because of approximations in there, because this assumes if you use a free energy barrier there, it assumes a quasi-static process. And it's not a quasi-static process unless you try really hard to make it a quasi-static process, which I did, and then you recover their predictions. Okay, but it's a special case, it's not. Cool. Yeah, this is really neat. And again, you can do escape over a barrier, and you can explore this conformalism too. And you can ask the question, well, how about if it's not a reflecting boundary condition, but it's an absorbing boundary condition? Okay. Which is actually true for the case of polymer translocation.
What's the name for this relation?
I don't know if it has a name. Winkel? That doesn't.
I claim it.
Therefore, I can.
Wikipedia.
Well, so like, how do we look it up?
I don't know. I can give you some papers.
Okay.
Just make sure you have edit privileges on Wikipedia.
Yeah. Cool. So this is non-equilibrium simulations, Monte dynamics, Brownian dynamics. It's all very easy. When we come back next week, we're going to look at Monte Carlo when we have external force in there. We're going to see that things are not so easy there. Okay, because we lost our equation of motion that we just add our forces to. We have to start playing with our jump probabilities, and you'll see that we actually have to be very careful. Cool. And this will lead nicely into our next talks about Monte Carlo. We're going to start looking at systems that we can define by Monte Carlo, and trying to get to low energy states, etc. And